Hello everyone. In this video, we will move forward to the chapter 1.2 where we will discuss about algorithms as a technology. Suppose computers were infinitely fast and computer memory was free. Would you have any reason to study algorithms? The answer is yes. If for no other reasons than that you would still like to demonstrate that your solutions, method, timeliness and thus so with the correct answer. If computers were infinitely fast, any correct method for solving a problem would do. You would probably want your implementation to be within the bounds of a good software engineering practice. For example, your implementation should be well designed and documented, but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they are not infinitely fast, and memory may be expensive, but it's not free. Computing time is therefore a bounded resource, and so is space in memory. You should use these resources wisely, and algorithms that are efficient in terms of time or space will help you do so. So, if we talk about efficiency, different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, in the future chapter 2, we will see two algorithms for sorting. The first is insertion sort and another is merge sort. So the time complexity of the insertion sort is big O of n square. So if we break down that, we can see a constant multiplied to n squares to sort n items, where C1 is a constant. I talked about it earlier, but the constant does not depend on n. That is, it takes time roughly proportional to n square. The second merge sort takes time roughly equal to C2 into n log n. Log n is log base 2n, and C2 is another constant that also does not depend on n. Insertion sort typically has a smaller constant factor than merge sort, so that C1 is less than C2. We shall see that the constant factors can have far less of an impact on the running time than the dependence on the input size n. Let's write insertion sorts running time as C1 n into n and merge sorts running time as C2 n into log n. Then we see that where insertion sort has a factor of n in its running time, merge sort has a factor of log n, which is much smaller. For example, when n equal to 1000, log n is approximately 10, but when n equals to 1 millions, log n is approximately only 20. Although insertion sort usually runs faster than merge sort in small input sizes, once the input size n becomes large enough, merge sort's advantage of log n versus n will more than compensate for the difference in constant factors. No matter how much smaller C1 is than C2, there will always be a crossover point beyond which merge sorts is faster. For a concrete example, let us pit a faster computer running insertion sort against a slower computer running merge sort. They each merge sort they each must sort an array of 10 million numbers. Although 10 million numbers might seem like a lot, if the numbers are 8-byte integers, it will only take 80 megabytes. Suppose that computer A executes 10 billion instructions per second, faster than any single sequential computer at the time of this writing, and computer B executes only 10 million instructions per second, so that computer A is 1000 times faster than computer B in a raw computer power. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort in machine language for computer A, and the resulting code requires 2n square instruction to sort n numbers. Suppose further that just an average programmer implements merge sorts using a high level language with an efficient compiler like Python or any other modern language we have now, with the resulting code taking 50 n log n instructions. which which seems much bigger than the 2n square, but we will see what goes in the future. To sort 10 million numbers, computer it takes. So after taking the calculations, the computer aid takes 20,000 seconds, which is approximately more than 5 hours and a half. While computer B takes, in spite of seeming a very large number, we can have only 1,163 seconds, which is less than 20 minutes. So you can see the difference between the two, where one takes more than 5 hours and another takes only 20 minutes, not also an hour. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more than 17 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 100 million numbers. When insert sort takes more than 23 days, merge sort only takes 4 hours. You can see the difference. In general, as the problem size increases, so does the relative advantage of merge sort. Algorithms and other technologies. The example above shows that we should consider algorithms like computer hardware as a technology. Total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Just as rapid advances are being made in other computer technologies, they are being made in algorithms as well. So, algorithm goes under much development like any other technology in today's modern science. You might wonder whether algorithms are truly that important on contemporary computers in light of other advanced technologies such as advanced computer architectures, uh, graphical user interfaces, object oriented systems, web technologies, and networking technologies. The answer is yes. Although some applications do not explicitly require algorithmic content at the application level, uh, but many do. For example, a web based service that determines how to travel from one location to another, its implementation would rely on fast hardware, a graphical user interface, and wide area networking, also possibly on object orientation. However, it would also require algorithms for certain operations, such as finding the smallest route, rendering maps, and interpreting addresses. So, here we can use a shortest path algorithm. So, we can say the system will use algorithm at some point. Moreover, even an application that does not require algorithmic content at the application level relies heavily upon algorithms. Does the application rely on fast hardware? The hardware designs used algorithms. Does the application rely on graphical user interfaces? The design of any GUI relies on algorithm. Does the application rely on networking? It is also using algorithms. Was the application written in a language other than machine code? Then it was processed by compiler, which is absolutely a extensive use of algorithms. Algorithms are at the core of most technologies we used in this era. Furthermore, with the ever increasing capacities of computers, we use them to solve larger problems than ever before. As we saw in the above comparison between insertion sort and merge sort, it is at larger problem sizes that differences the efficiency between algorithms. Having a solid base of algorithmic knowledge and technique is one characteristic that separates the truly skilled programmers from other novices. With modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much more. Here are some exercises you can work out to further explore the contents about algorithms and get used to some get used to algorithms as a technology. Thank you for your patience.